All right, Unit 3.2, differentiability. So before we get into the rules of derivatives, we have to look at what can be or cannot be differentiable. So that's what the objective today is going to be, to find where a function is not differentiable and distinguish between corners, cusps, discontinuities, and vertical tangents. That's what we're going to work on today. Day 2, we'll work on approximating derivatives numerically and graphically. So how f prime of a might fail to exist. A function will not have a derivative at a point P where the slope of the secant lines f of x minus f of a over x minus a fail to approach a limit as x approaches a. The next figure illustrates 4 different instances where this occurs. For example, a function whose graph is otherwise smooth will fail to have a derivative at a point where the graph has one of the following: a corner. So here we have a corner where the one-sided derivatives differ. So anyways, coming from the left, the derivative is negative. Coming from the right, the derivative is positive, and therefore it's going to fail. Corners are kind of obvious, and they're going to always be under an absolute value. So, or it could be a piecewise function as well, but if you get an absolute value, it's going to have a corner. Therefore, not differentiable at the vertex. So in this case, 0. The second one is a cusp. A cusp where the slopes of the secant line approach infinity from one side and approaches negative infinity from the other side, an extreme case of a corner. And so basically what they're seeing is, as it's getting closer and closer to 0, you can see that the slope is increasingly getting larger to the point that it looks like it's almost going to go into a straight line or even become that axis. So this is going to be the cusp. It looks like a corner, but not quite a corner. I do want to point out that what's going to happen is that your root will be odd, and up here the power will be even. So anyway, you have an even over odd power. That's a good sign of a cusp, because what happens is that it doesn't matter if x is positive or negative; it will always be positive, the value coming out of it. The next one is a vertical tangent, where the slopes of the secant lines approach either positive or negative infinity from both sides. So on this one here, as it's getting closer and closer to 0, you can see that it's starting to form a vertical line coming from the other direction as well as. Now I want to identify that this is equivalent to x to the 1/3. Notice that it's an odd power over an odd power. Is going to be something that you'll see on this, especially the 1 power. And so actually it's odd power over an odd root. You can get this. So like this is a square root of x cubed. And last but not least, a discontinuity which will cause one or both of the one-sided derivatives to not exist at all. So in this case here, coming from the right, my limit is 1, but coming from the left, it is -1. Therefore, it cannot be, I can't take the derivative at 0 because it's not defined. And that's what it comes down to, is that continuity idea. If it's not continuous, it's not differentiable. So on this one here, show that the function is not differentiable at x equals 0. And then they gave you these. So at this one here, if I was to take the derivative of this, basically what you look at this, you're going, okay, well, this looks like it's coming straight down, and then it kind of pops over. So it's really this guy I want to look at. Because we can't say it's not continuous, right? Because f of 0 equals 0, or I can do left and right limits. As the limit approaches from, this one's the left, so as the limit approaches from the left, I'm going to get 0. If it approaches from the right, I'm going to get 0. If I plug into 0 into this guy, I get 0. So it is continuous. You cannot claim it to not be continuous. But what we can look at is from each side what the limit's doing. So this guy here, as he gets closer and closer to 0, our derivative we can see is a positive value. But coming from this direction, our derivative, oops, this is a positive value. I said positive. This one's also a positive value. but they're not approaching the same direction because of this guy here is kind of doing a little curve in, which makes him a cusp. You don't even have to know how to find your derivatives yet. Well, I can tell you guys, hey, guess what? F prime of x is going to equal 3x squared when x is less than 0, and 4 when x is greater than 0. Well, guess what? I plug in 0 here. F prime of 0 here gives me 0. The F prime here of 0 gives me 4. This is what they're talking about, is that your derivatives are not giving you the same. So I can do the limit as x approaches 0 on F prime, and show the fact that I don't have the same slope at 0. Anyways, my slope changes at that point. So, but this one here is a cusp. What they're looking for is what's causing it to go bad, and it's the fact that I have a cusp here. Okay, so how will this one fail? What did I tell you got about absolute values? You're going to get a corner. That does not look like corner. Corner. There we go. You're going to get a corner. Because if I graph this guy, my vertex is going to be at 2, 3. My vertex is here, and it does this guy. I have a corner. And then the next one, the function fails to be differentiable at x equals 0. Tell whether the problem is a corner, cusp, vertical tangent, or a discontinuity. And I gave you guys a hint on this one. By the way, not discontinuity. I can put 0 in. I can put a negative value in. I can put, anyways, the domain on this guy is all real numbers. I can put any number in there I want. Okay, the vertical tangent, possibility, not a corner because that comes with absolute values. So it's one of these two. But this is the one that I told you to watch for an even power over an odd root. And that's exactly what we have. Therefore, it is a cusp. Okay, well, that's the end of day 1, and that went really, really fast, like 7 minutes. That's pretty cool, though. All right, so let me go ahead and get that video started.